Welcome, this is Mrs. Nearing, and in this video we're going to be talking about kinetics, which is the study of reaction rates, and we're specifically going to be looking at calculating reaction rates based on data and interpreting graphical data, molarity per second, and thinking about stoichiometric ratios of a reaction and how that relates to reaction rates. So kinetics overall in this unit, we're looking at the study of reaction rates, which is talking about how fast a reaction goes. So reactions might be spontaneous, which means they just, occur on their own with any kind of outside help, but they might occur very slowly. For example, rusting is an example of a spontaneous reaction that occurs very slowly. So when we're looking at reactions, there's two things we'll be thinking about, and one of them is, is the reaction spontaneous or not? And we'll get into that more in Unit 5 with thermodynamics and figure out why some reactions occur and some others don't. And then we also want to consider the rate of a reaction. And this is important because, let's see, thinking about in our bodies, chemical reactions control the metabolism of food, the transport of nutrients, the regulation of body temperature. And if food metabolism occurred at the rate of, rusting that train we were just looking at in that earlier picture, then we would not get the energy we would need and we would not be able to survive. So it's really important that these reactions occur at a reasonable rate. So that's what we're studying here. So some basics about rate. When we measure rate, we usually measure it in the change in concentration over time. So the units are going to be in molarity per second, or they might be in molarity per minute or molarity per hour, but it's always in concentration per time. And we could look at the rate of disappearance of a reactant over time, or the rate of an appearance in the product over time. But no matter if we're looking at the rate of disappearance of a reactant or appearance of a product, we always express rate in a positive term. So notice in this equation, when you're talking about a reactant, you take the negative change. Since the reactant is disappearing over time, the difference is going to be negative, and so you take a negative of a negative. It's going to give you a rate that's positive. So just keep in mind rates are always expressed in a positive value, FYI. So let's also talk about average versus instantaneous rates. So the average rate is something you might be more familiar with from previous experiences. You look at the change over a given time period. So the rate is just change in concentration over change in time. This would be like your, average miles per hour. If you drove 10 miles to school and it took you 30 minutes, you would take your, change in distance over change in time, and that would give you your average miles per hour. You could also look at the instantaneous rates, and that would be, if we're looking at our car analogy, like how fast you're going at a given point in time. Sometimes you're going faster, sometimes you're going slower. When you're looking at this graphically, concentration versus time, the instantaneous rate is the slope of a line tangent to the curve at that given point in time. And the instantaneous rate is going to change throughout the reaction. And we should notice, if you look at this graph right here, the tangent line is this line that you draw that is going to intersect your curve at just one point. So this red line is our overall reaction over time. Initially, the tangent, I choose a different color here. Initially, the tangent is going to be very steep, and over time, that tangent is going to get less and less steep. So, and eventually it's going to look pretty flat, so the rate's going to end up being 0 at the end of the reaction. So instantaneous rate will change over time. As the reactants get used up, the reaction's going to slow down because the reactants are going to bump into each other less frequently. So here's another example of this. You can see that if you want to measure the instantaneous rate at a given point in time, like someone says, what is the rate at time point 1? You would take the tangent and you would find the slope. And a reminder, the way that you find the slope of a line, it's rise over run, which means the change in the y value divided by the change in the x value. That's how you find the slope. And there's probably ways you can do this in your graphing calculator, but this is just the old-fashioned way to do it. So again, at time point 2, you'd say, okay, this is the instantaneous rate. You would look, what is the rise? So this would be the change in y, and you divide it by run, which is the change in x, and that would give you the slope. So let's look at an example of this. Here's a set of data. And let's look at how we calculate both the average rate and the instantaneous rate. So first, let's look at the average rate over the first 300 seconds. So the average rate is just going to be, the change in concentration divided by the change in time, change in seconds. So over the first 300 seconds, we're going to say the molarity went from, what did it go from? It went from 0.1 to 0.055, I'm going to say. It's somewhere in between 0.06 and 0.05. So I'm going to say 0.055. And then the change in time was 300 seconds. So I am going to plug that in my calculator. And I'm going to say 0.1 minus 0.055 divided by 300. That's going to give me 0.00015 molarity per second. You might also see the units written like this. I'm running out of room here, but molarity per second could also be written as molarity S negative 1. So writing S negative 1 is the same as dividing by seconds. And since molarity is moles per liter, you might also see it written this way as moles liter minus 1 S minus 1. Because molarity per second is basically moles per liter per second. So any of those ways of writing this unit would be perfectly valid. I'm just going to write it as molarity per second because I think that's the easiest way of thinking about it. So now let's look at the average rate over the first 900 seconds. This is still an average rate. You're just looking at the overall change in molarity divided by the change in time. And it looks like the change in molarity goes from 0.1 at the beginning to, let's call this 0.018. I think it's pretty close to 0.02 divided by 900 seconds. Plug that in your calculator. 0.1 minus 0.018 divided by 900, and you get 0.000091. And I want to point out, notice how the rate has gotten slower. So if I look at the average rate over this first chunk of time, it's going to be faster than my average rate over the whole reaction. That's because the rate slows down over time. So if you're averaging over a longer time period, we're going to see this average rate is going to be slower. So that's something to notice. And again, the reaction is going to slow down because the reactants are getting used up. They're not bumping into each other as often, so you're not going to get as many reactions happening. So now these are average rates. Let's look at instantaneous rates. So the instantaneous rate at t equals 0 seconds is the slope of this tangent curve right there. Let me actually use it in a different color here so we can see what we're talking about here. So this is the tangent line. And if you're doing this, you're actually going to draw the tangent, or if you're using a computer program, that's fine too, but this is the tangent line. It's going to hit your graph at exactly 1 point at time 0. That's the ideal here. And they're going to find the slope of this line. And the slope, remember, is rise over run. So change in y over change in x. So I'm going to take 2 points from this graph. Let's look at this point right here is at 0.1 molarity at time 0 seconds. And let's look at this point right here. So to find the slope, we can just take 2 points from our line. And at this point, let's see, what are we at? We're at 0.06 molarity at 200 seconds. And so to find the slope, I'm going to take the change in y. So that's, this vertical, the change in molarity. So it went from, 0.1 minus 0.06. That's the change in molarity. And then the change in time is 0 minus 200. And it doesn't matter which order I subtract these in, because remember, the rates will always be positive. So if I did that in the wrong order, that's fine. So let's see, 0.1 minus 0.06 gives you 0.04 per 200 seconds divided by, let me scoot back here, divided by 200, and this is 0.002 molarity per second. You might notice this rate is the largest rate we've calculated so far, which makes sense because initially that's when the reaction's gonna be going the fastest, because that's when we have the highest concentration of reactants. Later on, if we look at a different data point, like let's find the instantaneous rate at time equals 600 seconds, I'm gonna look at the tangent right here, And again, I'm going to pick 2 data points off of this tangent line. So right here, this one is, I'm going to estimate that being 0.042 molarity at 400 seconds. And this one looks like maybe let's say 0.018 molarity at 800 seconds. So the slope here, again, is going to be rise over run. So it's going to be 0.042 minus 0.018 divided by 400 minus 800. And if that gives me a negative number, I'm not going to worry about it because we always express rates as a positive number. Divided by 400. And I should get 0.00006 molarity per second. So notice how this rate is actually the slowest of the 4 rates we calculated, which makes sense because this happens later on in the reaction when a lot of the reactants have been used up. So there's less collisions happening. They're bumping into each other less often. Okay. Stoichiometric ratios. So stoichiometry is important in rates. So notice here is a 2 to 2 to 1 ratio between our reactants and products. What that means is that NO and NO2 are going to share the same rate. So NO is going to be formed at the same rate as NO2 is being used up. O2 is going to be produced half as fast since it's a 2 to 1 ratio here. And you can see this down here in the graph. You could look at the rate of NO and O2 forming, see that NO is forming a lot faster than O2 is, and it's because of the stoichiometric ratio. We can do some calculations using that. Here's a set of equations which might be kind of confusing here, so let's skip past this and look at some examples. So just think of it as mole ratios like you use in stoichiometry. So like here's an example. We got a chemical equation, and we know the rate of disappearance of one of the reactants. That's H+. And we know at a given point in time, the rate of disappearance of H+ ions is 0.4 molarity per second. Based on that, we want to calculate the rate of appearance of I3- ions. So it can help to label this. So we know that our rate is 0.4 molarity H+ per second. And we want to convert this into molarity of what? I3. So we want to say, what's the ratio, what's the relationship between H+ and I3-? Well, it is a 2 to 1 ratio. So I3 is going to be made half as fast as my H+ is getting used up. So my rate of appearance of I3 is going to be 0.2 molarity per second of I3-. So notice how H+ cancels out, I'm left with I3-. So it's just like a mole ratio you would do in stoichiometry. Let's do the same thing for another ion. So again, I'm starting with the same starting point. I know that the molarity per second of H+ is 0.4. I want to convert my H+ into I-. And there are 2 H+ for every 3, because I'm again looking up here at these coefficients there. In this case, it's a 3 to 2 ratio of I- to H+. So you're going to say 0.4 times 3 divided by 2 is going to give you 0.6 molar per second for I-. So you're just using mole ratios like you do in stoichiometry to convert between rates, just like in stoichiometry you convert between moles. You could also use this idea to identify which thing is which when you're looking at a graph here. So here's a graph and we know the chemical reaction between nitrogen and hydrogen making ammonia, and we have some data here and we're trying to figure out which is which. So which line corresponds to which reactant or product. And we're starting with equal amounts of N2 and H2. Can you identify which line corresponds to each molecule? So, well, our product is maybe the easiest one to spot because only one of the amounts is increasing over time. So your reactant concentrations are generally going to decrease over time, and our product concentrations are going to increase over time because you are using up reactants and making products. So therefore, the blue line here must correspond to my ammonia because that's being made. So I'm left with these 2 other lines. One must be N2, one must be H2. The difference is one of the lines is much steeper, so the black line is getting used up much faster. Looking at my stoichiometric ratio, it looks like I use up 3 H2s for every 1 N2. So my H2 is being used up 3 times. It is being used 3 times faster than my N2. Or for every 1 mole of N2 that gets used up, I use 3 moles of H2. So therefore, my black line must correspond to the H2 molecules because they're getting used up faster. My red line must correspond to the N2 molecules. And there's a sample problem from the homework, which is very similar here. The product is going to be the one that is increasing concentration over time. And then this one gets used up twice as fast as F2. So this one must correspond to this line right here, and this one must correspond to this line right here. And you could ignore this question about equilibrium. We'll come back to equilibrium later in Unit 6. So skip that one for now. And that is it.